So let's continue now with Yuriy Krustalev from Liquid.AI. Liquid.AI is an interesting new startup, also out of MIT. And Yuriy, I'll hand it off to you. I think you may be muted, Yuriy.
That's correct. That's absolutely correct. Thank you. In order to be here, let's begin. This would be a small talk about more on-hands experience and what others can learn, what we learned here, and maybe we will share something for the community next. Agenda is pretty simple. We'll speak what is Edge. There are many definitions, and I've heard few of them today, but in reality, Edge is something more and controversial, and you'll see, it's just amazing. Then challenges. How one who builds for the Edge, what would they need to consider? What is this? Resources, approaches. When you look at the guides in the internet, there'll be examples that mostly are incomplete. And it's quite difficult for someone who is new to this to start. We'll touch ExecuTorch and some simplifications on this. Okay, philosophical thing. What is edge environment? Is when I step out of a home, is it edge or not? We define here at Liquid that anything that has no PyTorch is edge. Because in PyTorch and VLM and all of these facilities and fascinating tools, you have everything for running a model. You don't need anything. So when you have no umbrella ML framework that is available at runtime, you're on the edge. Edge is when there is no CUDA. It's when you need to think how to perform, how to infer this data. When there is no, let's say, de facto defined easy way which works out of the box. I can go outside and I can get into the taxi, and it will be something like CUDA or PyTorch. But if I need to walk, if I need to plan my path, my way, no, this is the edge. There are constraints. So when you're operating on something where it's not infinite, when we look at the modern GPU boxes, a lot of memory, a lot of GPU, a lot of compute resources, you can do many things and you can be inefficient. It's already working. But on the edge, in order to get something barely working, you have to invest a lot. You have to do some work and efforts just in order to run something on a very simple, primitive level often. Also, on the edge, you're restricted. The operational system that you're running is likely some closed source or semi-closed, and you are forced to packaging solution. You need to bring everything from where you compiled it. You have to be tiny. You have to be self-contained. You're limited. And often the edge is not about just endpoint. You're part of some application. So there is someone else who has a business need, who has a particular idea they want to evaluate. They are using this edge deployment as the part of their application. So you're constrained from different sides and you're offline. You literally cannot utilize other box. Well, obviously one smaller box can use some bigger box and so on, but there'll be some place where we would say this is the end. You cannot go to the internet. You cannot use anything but this computer, these resources, these GPUs and CPU, everything. And it all leads to the following characteristics of your solution that you'll be working on the edge. It would be very tailored. So you cannot build something that supports all the backends, all different types of inference. You will pick a few, maybe one, likely one, maybe two. It's not designed for fine-tuning training or anything like this right now. I hope it will, but once we are there is no edge in the previous sense. So on the edge, when we are doing the inference only thing, we are decision makers. We are in the final stage. There is nothing then if our model returns something and it's convincing us, and it just says get it to the user. You have to get it to the user. There is no other way you can work around this. It's very hardware specific. So we will talk about different vendors, providers, and a lot of them are today available in this conference, which is great. And they're all actually quite different. Despite they're trying to achieve and solve this similar problem, the way how their software and hardware works is quite different. So the edge solution always tries to match the particular instruction set, particular memory model, particular I/O capabilities, particular all of these restrictions. ARM is a good example. When you have ARM and you have x86, you have differences. Some operations may work differently. They may be different precisions. They might even have errors, because if you're relying on a third-party library that is built for a particular assembly and it's rarely used assembly, it may contain error. You have to optimize and think about being limited all this time. So, good example, your model is quantized. You just cannot simply afford it as is. Your context window is limited. So if it's a KV cache-based model, transformers, you cannot accept infinite window. You're limited on this. And your OS, they will always get you that an amount of cores you can use, amount of memory, background process, all of this, always limited. Also, it's a different mentality of whom you're building this for. You are an entrepreneur in some way, because you have a client and their client have their own client. So you're likely building for an app developer who is serving some end user, and hence you need to be convenient for them so they can use you, and their application quality really depends on your quality of your inference, on your solution. You're the tool. And probably the most interesting aspect at looking at the edge is that you are measuring the model. If your model worked great during the training time and in the GPUs where you measure against other models on different arenas, and all look great, but after doing this, lowering to a particular backend, quantizing, limiting the context window, it may turn out that the quality of the model is very different. It's not the same. And you cannot claim to someone, our GPU worked great. No, it doesn't matter, because your final deployment is on this device. And if this device doesn't perform well, that's the model. So what is the interface? We're quite in an age of modern internet where everything is internet, distributed systems, networks. But there used to be a concept of complete software where things were not updated at real time. They would be implemented once and living in this state for years. Now, every day you receive a new version of something, and it's very easy to live in a GPU world on a server side, as you can deploy any change anytime, obviously. On the edge is different. You're planning for getting this thing to be untouched, staying for a cycle, 6 months, year. Oh, at least it's not daily. So whatever you plan, you have to think, what is my interface? How I expose whatever my inference engine is. And we know there is a good protocol, OpenAI. A de facto is a protocol everyone uses. They chat completions. The only downside is that it requires the internet, so we need an HTTP. Yeah, you can run it locally, but you then need to expose local host. You can force the client application to use it. Maybe they cannot. Maybe there are constraints on the devices that you cannot open the port. Maybe it's iOS and so on. So you need to think of different type of interfaces. Command line interface, probably the best interface that humanity invented since the beginning, and chat API, chat completion is literally the command line interface continuation here. And you need to think of it, how I can have my tool, my model being interacted where the only thing is bash or something that is limited and acting like bash. Obviously, the C interface, with it you can try to incorporate your engine whenever you can, anything, because the definition of the operational system is a need of the C compiler. Often, I think it's the reason all this operational system exists. So if you have the minimal bare bones C interface, now you're deployable almost everywhere. For the benefit of bigger applications, C++ interface, this is more interesting, because now you can think how I can get my model available on Swift, Apple, Qt, Windows applications. It's very essential. You don't want your app to be so isolated, your inference so isolated that someone who uses it needs to now pack two different things. You want to be embedded. And GNI is another example where we have Android application and you want from the Java or Kotlin layer pass your invocation down to the C and then to whatever you implemented. And here is a small diagram that shows you that the main idea I want to hear you take away from this is that inference engine is something that has interface, and there should be more interfaces than you think. And the lowest, probably the lowest level interface is the C interface. And then everything else is being built on top. And Llama CPP does a good job on this. Now let's look at consumer devices. So it was a fascinating 15 years since the Android and Apple iPhone were released, and they're competing, they're producing something new. And what we have right now is this matrix, a table of a platform, the architecture, flavor, and possible backends or engines that they have for executing some compute-intensive tasks. Let's just pick a few of them. Android. We all know Android as a consumer thing, and there are ARM8 is probably the most popular architecture and flavor. And there is a great company, Qualcomm, who've been here today. They have their Edge SDK. But also there is an XNN pack framework by Google that allows executing all these ML operators on purely on a CPU. But there are also less known things for Android. Is ARM7 or x86-64 for the simulator. And if you take into account, okay, I want to get my app that I am an end developer creating for my consumers, and I'll be using some ML tool and I would need an inference engine incorporated. And if I build it, now I need to think about 3 flavors. And if I'm using different backends like XNN or Qualcomm, this is multiplied now by 2, so it's 6. You see that complexity evolves immediately, and we just touched Android. If we go further, iOS, Apple, a great company, but also they have quite steep complexity. If you look at the number of flavors they support, so iPhone, they have a simulator. Simulator has 2 flavors. The iOS is single flavor, but Mac and iPad, they share something called Catalyst, so where you can use iOS UI tools for the Mac, and they're built differently, and they are technically different flavors when you compile them. With Apple ecosystem, we get about 7 flavors just to cover all the common platforms they support. But if we, on top of this, incorporate CoreML, which is the framework from Apple for computing-intensive tasks, and XNN pack as an alternative that works on a CPU, now it's 14. And this grows. We have a huge evolution of Windows with recent, again mentioning Qualcomm Snapdragon, but with AMD as well, the AI chips, that your computer becomes something capable of running this inference locally. And there is a divide, there is a split. So modern Windows computers are more likely to be more performant if they are using Arch64, which is ARM-based. And if you try to compile the same software for Windows, it's already a challenge when you have something that is originally designed for Unix to be precompiled on Windows. Now you have two different platforms, and you have Qualcomm, AMD, XNN, and possibly more to follow backends here. Just mention for the sake of existence, Raspberry Pi. It's a great platform because Raspberry Pi 5 can handle about 10 token a second 1 billion model if you compile it correctly using just XNN pack backend. And speaking of regular Linux, well, it's probably the easiest platform to support because it just works out of the box in most cases. But what is this thing in terms of a development? You are a developer. You are reading another how-to or manual on the vendor side, and I would say, our something runs only on this Windows, or on this version of Windows, or only on this particular Linux distribution, and it becomes hard. How you can cross-compile it? How you can cover this table by the software you developed on something just one flavor? How you can make sure that things that you develop locally would be possible to execute on all of them? You need to verify it somehow. But before, let's mention other things that an edge developer and we're Liquid, we're very concerned of, and we think the things should not be viewed distinctly. They are related and they are the inference. It's just they are not mentioned often, but let's mention here. We know that there is a forward method, but it's not always only the forward method that you need. You need the way how you transform your inputs. So maybe there is embedder that exists that translates your original consumed from the client side input into something your model understands. There is always a tokenizer or a set of tokenizers. It's not common that we probably public narrative says one model, one tokenizer, but not always the case. Sometimes you want to build something more complicated, and there are reasons for this. Multimodality, for example, or switching the models depending on a particular input. And tokenizer may be designed for a particular language that is not popular, for example, English, but you may even want to produce your own language and your own tokenizer. So a good example might be function calling, where you have some functions defined as tokens and their inputs or their arguments also as tokens. So you get into special token metrics and so on. You don't want to limit this. You need to consider it as something that is bound to a model and is distributed next to the model. So meaning that tokenization process and de-tokenization process is part of the inference. And it's not just you taking something from the shelf. Maybe you have to implement your own rules. Maybe you need to have post-processing in order to all of this make sense. Grammar manipulation. So there is a new trend in the AI ML industry where you just say it's not about what is the capital of France, but I want to get a very precise answer. I want to have a JSON where it would be just city and then Paris. I don't want the model to return me back some text which is has some temperature, some randomization in it. And here grammar things come in place. So now you need to think how I can run my model so that I can take the logits which are produced during the inference loop on a single step and tweak them according to the rule set which is grammar contains. And that literally means you need to hook into the process where the loop happens. Most of the frameworks, they're keeping you distant. They're saying, well, You can do this, but here is a DSL, or domain specific language, some way you tell our engine to do this, and our engine does it for you. But it turns out that you can actually look at it more deeply and closer and implement everything in a single subset of a language that would run on all of the platforms. Sampling. Another thing I mentioned, that if you look at the Llama CPP as an example, you'll find there are a few sampling tactics, but not necessarily your solution needs them. Maybe you need something else. Again, from a consumer standpoint, it may be not that obvious, but there are more than just top end. There could be low M and different temperatures and different ways how you want to eliminate particular tokens and so on. You want to multipass maybe. Back to the HTTP interface. So we know there is an OpenAI thing, but my small inference on my smaller device, maybe I want more than this. Maybe I want gRPC. Maybe I want to have specific authentication. And all of this need to be considered. How to get it, how to incorporate it and make it part of this deliverable file system. Just simply remember in C++, only CPP17 added the file system. So the common, before this, you had to use boost or some other techniques how you operate with how you deal with the file system in your particular case. Looking further, okay, there is Android, there is iOS, and they handle it very differently. You need to obtain permissions, you need to get things incorporated, handled properly. There might be caches, there might be some other restrictions. Your model, how you distribute it, how you load it, what is the process of obtaining it? Will you have an HTTP connection during the inference? Like Llama CPP offers us, you can say, this is the Hugging Face place, and you can pull it and then invoke it. But what if you don't? What if you need to have it ahead of run, where you store it? Maybe your model is trained on some private data. It was mentioned RAG many times. We know that RAG is a technique where you can inject something that is not meant for someone else's eyes. But sometimes you maybe have a model that is not public in some sense. Its architecture might be public, but its data, it's not. And you want to protect it. You may want to encrypt it. You may want to have some layer of security so not everyone can use it. And usually inference doesn't solve it. But just coming back, how you build a full solution if you have all these pieces in mind and you need to incorporate them all in once. Not even speaking of memory. So the memory, and we all know that if you're running Android, it can decide that if the application is too memory consuming, it could be killed. So you lose efficiency. How you can restore it quickly, how you can eliminate recalculations. We'll speak of this. So compiling all of this together is a challenge. And if anyone tried doing a pull request to Llama CPP would know that a full cycle of executing all the CI would be about 9 hours. And if you try to do this privately, it would cost you about $200 because of the time the GitHub will consume. But here at Liquid, we came up with a more simple solution. We built about maybe 10 flavors because of those we need. And we have 2 minutes in average for a build. And we have all the main platforms covered because our developers using Mac, Linux, and even Linux subsystem on Windows. So we have a minimal core, and we have independent, the baseline, which is independent and doesn't depend on anything platform specific. If you try to get all the mentioned pieces assembled together, you'll find that you cannot do this in a single code base. You'll have to borrow something from the community. You'll have to integrate dependencies. And those dependencies will likely have issues compiling on a different platform. So we'll end up with a different CMake or whatever tool you're using for this, because it's likely C++, or maybe C, but likely C++. And you'll have to think how to arrange it, how to structure your build system so that it's actually manageable and works, and that you split things that make OS independent work and merge it with things that are doing platform dependent work. And it's quite complicated looking at the table. So we came up with a unified low-level inference. The approach is straightforward. Let's build around some known framework and enrich it. So C, C++ are the obvious choices because of the XNN Park and other things. We're using ExecuTorch. I'll mention it further. Rust. What we noticed is the whole ML industry goes towards Rust, and vendors really need to consider making the bindings towards Rust, because otherwise the community tries to build them themselves. And there is an additional layer, that boundary where you need to copy the data back and forth. But don't underestimate using Rust from the beginning. It will be much easier by looking at the scope of things you need to accomplish. You have to be cross-platform, and we do our unified low-level inference cross-platform, so that anyone who develops in the same on a different machine, we expect it to run in a similar way, obviously using the same backend on different machines. Make the inference, you need to make the inference a model agnostic, so that OpenAI has this chat completion specification, and it actually covers all the modalities already. So there is a way to pass an image, audio, and text, and their combinations. And I don't think there is anything better than this on a simplest level. Obviously, there are MCP and other protocols that would be agent specific. But looking at this, you can achieve by mimicking what is there. And then it's very easy to use the existing tools which are tailored for this OpenAI compatibility. Not mentioning the our tool also adds some premium feature, I would call them, is lifecycle and orchestration. So some of the talks mentioned about distribution of the things and making actor-like architecture where something acts, keeps its state, shares the state. This happens on a device as well. Simplest way to look at it is when you have a device and it boots up, you need to consider whether I'm loading a model or not, whether the model is always in a hot state and is available for the inference, or it's loaded on demand. And it's a decision that every developer makes on their own, but it's not something that any current solution on the market actually suggests you how you do this. Power management. Looking at all these devices, you may not notice that if you don't tweak them, they would be slow. So very likely that if the plug is not there, or by default any Android phone would be saving power, you need to enable it programmatically. There are ways to do this. Simplest thing is increase the thread priority on the inference, so that whatever you do, whatever you're trying to compute, takes the priority and makes it the fastest as possible. Throttling. All the devices actually have throttling. And it's not something you would find easily achievable and accessible on the internet how to solve it. The problem with it is that you can even put on throttling a bigger server with 90 cores with the needed set of a load. Sandboxing, provisioning. Is the target OS you're trying to deploy ready for your application? Are there missing C Linux or other type of privileges that you're missing? How the scheduling works? Would you need to tweak a particular deployment so your application, your inference gets the best scheduling policy? All of this is covered in the platform. So, how to get to the edge? You have an idea, well, perhaps you have an idea of the application that you have a target audience. Well, you have two ways in general, to my mind. Maybe there are more. Well, there are definitely more, but main two open source things. First, we usually have a model defined in PyTorch. Well, obviously there are other frameworks, but if you define something in PyTorch, you probably can take it, or in Ajax or TensorFlow, you can define it in a PyTorch. It's your canonical way of your architecture, and you train in it. Again, if you're using a different fork, it doesn't really matter. The main point I'm making here is that there is something Python, and there is something science specific that is easy to use, which is absolutely unsuitable for running on the edge. Then how to get to the edge is two ways. You either export it in some form, and PyTorch has ExecuTorch, where it traverses the graph with a sample input and tries to figure out all the operations that are needed and builds this graph for execution. So in the end, you get a flat buffers file which defines all the weights and all the chains of execution. Second way, you go with Llama CPP and GGF. You implement the model in a C++ inside of the Llama CPP. And then you assume that whatever backends and operations that exist in your model are intersecting, then that's the number of platforms you support. For quantization, you need to choose. You cannot afford a model as is. And it's a matter of trying back and forth. And it's somewhere between int 2 and maybe int 8, and in some cases FP16, where you would say, this is the quality that I would accept for my model. And it really depends on the also hardware that you target. Some of the devices may not support in 8, some of them may not support in 4, and so on. The optimizations also hardware specific. So if we look at the XNN, and there will be many kernels for instruction set from ARM to x86. And you have to choose which of those you want to apply. So enable the flags. In fact, if you're compiling for your edge on a hardware that supports more flags than, well, I'll take it this way. Sometimes you may find that when you compile a particular backend like XNN, if you don't specify flags, it will try to get these flags based on the current continuous integration machine, which might be wrong, because the set of flags that you would want to use on a target deployment might be different. And you might consider limiting them from the beginning, because the numerical correctness is not always there. We're still in the process of getting this matured, but we still observe a lot of issues as an industry and all of these frameworks that something doesn't work on a less popular platform. So we picked ExecuTorch, and it's our bridge between the science and efficiency that they can get. Our science team, they're experimenting with operators, with layers, and they want to get a quick turnaround of how it acts actually on a target device. So if they were to use Llama CPP, they would have to first come up with a definition in Python and then implement the same thing in C++, which is obviously would take more time. But with ExecuTorch, what they can do is make a tweak, export, and quite fast get something compiled for the target platform and measure it. So it's not just theoretical results, but efficiently knowing how it acts, how it should be. It's very fast. And the faster you can iterate on this, the more successful you are in achieving your model capabilities. Memory management. One thing that, as we all know from the past, from the web services, that efficiency comes from caching. You just don't calculate something. For those who work with Llama CPP know that there is a KV cache and there are approaches where you can sort of use slots and load, store, but it's quite complicated when it becomes non-transformer based architecture. With ExecuTorch, there are ways how you can efficiently manage the memory by splitting the allocations of the memory per region. Example, Liquid model is a combination of KV cache and SSM state. And with ExecuTorch, what we can do, and you also can do with your model, it's not something unique to us, you can change the way this memory is grouped, and you can come up with different regions with activations, caches, and SSM caches separate. And then it means in your model during the inference, there would be an immutable state and mutable state. And mutable state is actually very small. Here is an example on this screenshot that 1B model, which is about 1 gigabyte of data, the mutable part is just 70 megabytes. And for the 3B model, which is a bit more than 2 gigabytes, is about 200 megabytes. Which means that on the edge, when we build this solution, we can achieve the edit functionality. You know, when you open the chat in Gemini and you type something, but then you return to the previous message and you say edit and tweak it and reiterate. So you're using the previous steps as a memory and then adding some, you're branching effectively, forking your way of conversation. You can do this on the edge. You can do this already today. And it's quite efficient. You are trading the disk space to the prefill. Again, many people would not, they do not see this from the beginning, that when you're working with a GPU, your the way how you prefill is so fast that it just doesn't make any sense to cache it sometimes. On the edge, it would be about speaking from minutes reduced to seconds. So obviously, if you have something that is big enough and it has to be pre-filled for 2 minutes, you'll have to do this. It might be a set of rules, might be a set of the original system prompt that contains more personal information or something like this. But if you're able to cache it, and as I mentioned, cache here is very tiny bit of the space, you then can start your new conversation always on this cache. So making you're achieving something, you're eliminating pre-calculations by invoking this, and ExecuTorch is great at this. Okay, double slide. With ExecuTorch as well as Llama CVP, you can get your custom operations. So it's when you're looking at a model and a scale and it looks good in Python on the GPU, but then turns out there are so many operations, so small operations that maybe they should be just swapped into a single C++ function that just encapsulates this and the whole layer is there. And again, as Llama CPP, your way is you implement everything. So you keep two sources. You have your maybe Python imaginary source where you train, and then you always adapt it. And there are some companies that are liking doing this, but with ExecuTorch, you can always export, and you can even achieve the way where you would define a whole function, whole layer in C++, and just expose it to Python back. So whenever you are working with PyTorch, you are invoking the actual C++ implementation. So you're basically operating in Python, the C++, which is fast. And it's cool because your iterations are fast. And whoever is familiar with C++, again, it's not that complicated. It's about just kernel, few vectors that you need to do some operations on top of them. And it becomes a matter of maybe seconds, maybe minute, less than a minute. You can do back and forth. You can make those backend aware, and you can even have a set of the same operator implemented for different backends with different delegation, which is again very cool because it's just simply on the Python level, it's the same invocation, but on the implementation level, it's per backend. So you shift it towards the library to pick the right implementation. And it makes all of this prototyping and production much easier. Here is the snippet where in Python, I'm literally copying the code from our experiment Git repo where we're loading just lib, and you see the star in the end. In fact, if we compile this for Windows or for Linux or Mac, it all works all the same. So we have people on different OS, and we are able to use Python this way to speed these things up. Another thing we do, and I think the industry will get there, is I mentioned it as well. When you're working with a model on the edge, it's not just the model, it's a set of files associated. It matters because your model might be a set of smaller models that have built a graph on different conditions, or you have a customized tokenizer, embedder, or you have multiple models, or other things. And we have a GGUF format available from Llama CPP, and by looking at the ExecuTorch and the PTE file, which is a flat buffers, you can extend them, and we incorporate more information in order to know what was the quantization, what was the original model, what was the path, what was the SH256 of all the files related, and so on. Why am I telling this? Well, one may ask how we get there, how we can try using something like this and deal with the complexity. And Liquid soon is going to present a platform. It will be called Liquid.AI Edge Platform. Yeah, I know the name is not the greatest at this point, but we will try to get the things as easy as possible, where the Edge developer, the final application developer, would be given all these tools and even maybe precompiled binaries or sources and instructions how to build them on their own and just incorporate into their application. We see a traction of Google presenting similar to this. Telegram today announced working with Grok. They're not Edge, but perhaps they will. So we're proposing to have smaller models that are available on different quantization layers, and they're available on the edge with all these described tools in all flavors, meaning that if you pick just whatever application you want, you will get a similar experience and result using this application and this tool. It's not yet there. It would be announced separately, but from my side, it's probably it. Thank you for having me there.